About the product rule, I hope that you are a little bit convinced by now that even though the statement was very trivial, we just want to distribute some marbles in some boxes. We have 5 boxes, 3 marbles in each, and we have 15. But it was more interesting than this. We were able to solve more interesting problems than just this statement. And now this is also true for the other rule that we have, and that's called the sum rule, and that would be the topic of today's lesson. And then of course the examples, the nice examples are combinations of the sum rule and the product rule. And you need, now it begins that what I have said before becomes very important. So if you haven't used to think about the product rule in the way that I described it for you, then it would be a little bit problematic. Sometimes people confuses when we should use the sum rule and when we should use the product rule. But if you have learned it in the way that I described it, hopefully you will not face any problems. Okay. So apparently this is, I have I don't know, I have 3 bananas, I have 5 apples. How many fruits do I have? I have 7 fruits, yes. I don't know what I said. 2 bananas and 3 apples, then I will have 5 fruits. That is exactly as simple as this again, but then it becomes a little bit more interesting when we go to the problem. And I remembered I just gave you a problem at the end of the last session. Okay, if we have time, we will go back to it. We were supposed to show that for any set, the number of subsets with even number of elements is exactly equal to the number of subsets with odd number of elements. I don't know how many of you have thought about the problem, but that is also a very nice problem. Okay, so let me start with this lesson today. So the sum rule. If a first task can be performed in n sub 1 ways, while a second task can be performed in n sub 2 ways, and the 2 tasks cannot be performed simultaneously. So this is the key to this sum rule. Then performing either task can be accomplished in any one of n1 plus n2 ways. So I'm not saying that accomplishing the task can be broken down into several stages. In the product rule, we break down the task into several stages and we do them one by one, and the whole task is accomplished only if the whole stages are actually accomplished. But here it's a different story. So here we have a task. It can be, there are actually 2 tasks from the beginning, okay? One task can be done in n1 different ways, the other task can be done in n2 different ways. Either of these tasks, not them simultaneously. According to this condition, they cannot occur simultaneously. Then if I want to know in total how many ways I can do either this task or that task, and if I know that these tasks cannot happen simultaneously, cannot be performed simultaneously, then there are n1 plus n2 ways to do this. And as a remark, exactly like the product rule, that we started with a task with 2 stages and then we extended it to a task with more than 2 stages. We can also immediately extend the sum rule to more than 2 tasks. But the point is that if I have 3 tasks, none of them can be done simultaneously. No two of them can be done simultaneously. If that's the case, then the number of ways that I can do either one of these tasks is n1 plus n2, for example, plus n3. Okay, let me start. Instead of talking, let me just start with a very simple problem. There are 3 roads and 5 airways connecting 2 cities. In how many ways one can travel from one city to the other one. Yeah, very simple, yes. So here there are two tasks from the beginning. Okay, so we can either choose a road to travel, or we can choose an airway to travel. And usually, yeah, this cannot happen simultaneously. If you choose a road to go, then you are there and the task is accomplished. Your task is actually going from city 1 to city 2, but you can do it in either two ways. Either you can choose a road or you can choose an airway. The options in front of you for the road, according to the problem, is 3, and the number of airways that you can choose to go from city 1 to city 2 is 5. So how many options are in front of you? You see there is nothing to multiply. We have to add these two options, as simple as that. Okay, so then I would say that the answer to this problem is we have 3 roads in front of us, and then we have 5 airways in front of us. The task going from one city to another city is done if I do it in any one of these ways. I don't need to do it in both ways, and actually I cannot do it in both ways, because as soon as I choose a road and I go from city to the other city, then I am done, task is accomplished. Or I can regret and go back and actually start to go with an airway. Then I have 5 options available, and when I do it, I go to that city, I am done. So the total number of ways that I can choose to go from city 1 to city 2 is just 3 plus 8, 5. Yeah, I hope that this is understandable, that there is no product involved in this problem. And the answer is simple as that. Okay, let us go to example number 2. And whenever you have questions, please interrupt me. How many numbers can be written using 1, 2, 3, and 4? Okay, let us just stop here. How many numbers can be written using these numbers? How do you look at the problem? If you want to look at this problem, by reading this statement, you see that, of course, this is a little bit ambiguous. I should have mentioned, yeah, I think this is not exactly correct. So how many numbers with at most 4 digits can be written using this? So let me write here. Okay, I will fix it, and when I wanted to upload it, I will correct it. Okay, so how many numbers with at most 4 digits can be written using 1, 2, 3, and 4? Okay, so if I want to look at the problem, because I have at most 4-digit numbers, so it means that might be I can choose only 1-digit numbers, or 2-digit numbers, or 3-digit numbers, and finally 4-digit numbers according to the problem. And the point is that if a number is 1-digit number, it cannot simultaneously be 2-digit number. If a number is 3-digit number, it cannot be simultaneously 4-digit number. Yes? So it means that the way that I have to look into the problem is something like this. So for example, you can assume that you have a rectangle containing all 4 digits. So I would say that numbers with at most 4 digits, written using 1, 2, 3, and 4. Okay, so you can imagine that you can partition it. Don't worry about the sizes, I don't care about the sizes, but I can partition this into 4 categories. Yes, so I can say that 1-digit numbers, I count the number of 1-digit numbers, then I count the number of 4-digit numbers, then I count the 2-digit numbers, 3-digit numbers, and 4-digit numbers. Yes, so here I would say with 1 digit, let me write it simply, 1 digit, and 2-digit numbers, and 3-digit numbers, and finally 4-digit numbers. it is completely clear that if I know how many items are here, how many items are here, and here, and here, I just add them. You see, there is no multiplication going on. But for calculating the number of elements in each one of these parts, you might need the product rule. Okay? So today's lesson is telling me that I know that the whole set can be partitioned into 4 subsets, but they are mutually disjoint. It means that there is nothing in common between these two, between any two of these parts. Yes? So this is it means that if I know how many are there, how many numbers are in this part, how many numbers here, how many numbers here, and how many numbers here, the answer to this question would be, of course, n1 plus n2 plus n3 plus n4. Yes? But n1 is clear. Let me move it a little bit to leave some space for the other one. So what is n1? n1 is clear. I'm allowed only to use 1, 2, and 3, and 4, and then I want to see how many one-digit numbers are there. So clearly 4. Either 1, 2, 3, or 4. But for calculating the number of items in n2, I have a 2-digit number. Yes, so I have a two-digit number here. And then for the first one, now I have to use a product rule to answer n2 itself, because I would say that I want to construct a 2-digit number, and the digits are supposed to be chosen from these 4 possibilities. How many options are available for the first one? It's 4. And how many options are available for the second one? Again 4. No restriction, so this becomes 16. And finally, for example, next one, n3, I have this. I want to write 3-digit numbers, and then of course again I have 4 options available here, 4 options available here and here, so it is 64. And finally n4 is the same story. Yes, so here I have 4, 4, 4, and 4, so this becomes 256. So the answer that I write here is 4 plus 16 is 20, plus 64 is 84, plus 256, 84, so it is 340. Yes, 84. Yes. But then if I want to answer this, the next part of the question, what if repetition of digits is not allowed? Then of course again the first part doesn't change at all, but calculating each part based on the product rule will change. Yes, so again this time let me write the question mark. This time let me write it as n1, n2 to make a difference between the symbols, n2, n3, and n4. But this time when I want to calculate n1, of course this is exactly the same. If I want to calculate n2, then I will have 2 tasks to be accomplished simultaneously. The first one has 4 options, the second one is 3. There are 3 options for the second one because repetition is not allowed, so this becomes 12, and n3 becomes 3 of them. Yes, so we have 4, 3, and 2 because repetition is not allowed, so this becomes 24. And finally n4 is also 24. Yes, so this is 4, 3, 2, and 1, which of course again becomes 24. And then the question mark becomes 4 plus 12 plus 24, which is 40, plus 24, which is 64. So of course this is a very simple problem, but this captures the main essence of these problems. Usually one rule is not enough to solve the problem. You have to use both of them. Okay, let me solve another simple example. Then I will give you a list of problems and I will wait a little bit because there is nothing to it. You need to get used to this way of thinking to be able to solve these problems. So example number 3. There are 5 red, 4 green, and 6 black different cards. All of them are different, so even the red ones are different from one another. In how many ways can one choose 2 cards of different colors? Okay, so how should I do that? Any ideas? The question is very, very simple, but I hope that you are not confused. You don't need to give me the answer, just give me how do you think about the problem.
We can think of it as a two-step task. First we choose the first card and then the second card.
Okay, do you think that this will work? That is exactly this problem. This problem is actually a simple problem, but I think it captures the essence of these. These problems are simple, but I want you to differentiate the difference. Okay, I'm not saying that what you are saying is wrong, but you need to defend yourself and continue, okay? So you say that you have 2 tasks, yes? You want to choose what? Okay, can you define your task and can you define the stages of your tasks if you want to do it using the product rule? I don't know if you want to use it the sum rule or a combination of them. Yes?
Should it be that we have 4 tasks and the first task decides which of the other 3 to use. So we have 1 task for choosing the second card if the first card was red. We have 1 task for choosing the second card if the first card was green, and we have a third task for choosing.
Okay, you are more or less right, but let me say something. Just take 1 minute to give me the final number. In how many ways can one choose 2 different cards of different colors? Even the red cards, I emphasize, even when I say I have 5 red cards, assume that they are 5 different red cards that I can differentiate. So all these cards, these 15 cards, are completely different, but they have 5 of them are red, 4 of them are green, and 6 of them are black. Anyone can answer. What is the final answer to this problem? There is a number.
I would say it's 74.
Yes, 74 is the correct answer. Thank you. So, because if I want to choose, when I say I want to choose each one car, I want to choose 2 cars of different colors. But how many options are available for me because of saying different colors? One possibility is to choose a red and a green car. A red and a green car, yes? So I would say that one option when you say different colors, I can choose 1 red, we can choose number 1, 1 red and 1 green. Or 1 red and 1 black. The reason that I am writing because I want to tell you something. Or 1 green and 1 black.
Baba,
Yes?
so could you just do like 5 times 4 plus 5 times 6 plus 4 times 6?
Yeah, exactly. That is the answer. It becomes 74. Yes. That's the correct one. But I want to describe it. This problem is simple, but I want you to understand everything. And I want to emphasize on these words here. Before explaining about this, but everybody agrees that we have three mutually distinct options available. If I choose one red car and one green car, my task according to the problem is accomplished. Or might be I choose a red car and one black car and then I am done. Or if I can choose one green car and one black car, then I am done. And then this option number one and option number two are distinct these choices are distinct choices because I cannot simultaneously accomplish this and accomplish this. Because when I accomplish this, it means a red car and a green car is chosen. Simultaneously, I cannot choose a red car and a black car if I want to choose two according to the problem. So I want you to understand these tasks are mutually distinct, or disjoint is better, mutually disjoint tasks. They cannot be done simultaneously. But forget about these. How many options are available for first part here? You say that I want to choose one red car and one green car. So this is a product rule. Assume that you only have red cars and green cars and I ask you to choose two cars, one red, one green. How many options are there? This becomes a product rule. So you would say that 5 multiplied by 4 is 20. In 20 ways I can choose a red car and a green car. In how many ways I can choose a red car and a black car? This number of ways. And in how many ways I can choose a green car and a black car? So this becomes 24. But how many ways I can accomplish this task demanded in the problem? 20 ways is acceptable, 30 ways is also acceptable, all these 24 ways are also acceptable. So the answer to this question is the sum of these, not product. So this becomes 20 plus 30 plus 24, which becomes exactly as YouTube predicted, 74. And now I want to draw your attention about these connectives. Usually and signifies a product or signifies a sum. Okay, so this is more or less always the case. So if I read it in this way, I can choose a red car and a green car, or I can choose a red car and a black car, or I can choose a green car and a black car. So more or less automatically it becomes clear what to do. I need to use product rules for the ands. I need to use the sum rules for the ors. So that is actually a rule of thumb that you can just follow. Okay? Any questions regarding these three problems? Okay, so now I want to give you more or less half an hour to solve these problems, and please try do it until the end so that you can get a number at the end. Then we can check together, are these numbers correct or not. Okay, so examples 4 up to 8. So now let us start solving the problems one by one, and this will end the meeting today. Let us go to the next page, do them one by one. Okay. Any answers for the first one?
I got 328.
Anyone else?
I got the same.
Yeah. Yeah, okay, so that's correct. So 328 is the correct answer. But the important thing is to realize that you indeed need the sum and product rule together, yes? So I want to describe it a little bit here. So here it doesn't work. Even if you change the order of stages, it's actually inevitable. You cannot avoid the sum rule. Okay, so might be let me just give you the solution first, so that everyone see that everyone agrees or not. So here I want to accomplish writing a 3-digit even number without repetition of digits. Okay, so my task, so I can just do it like this. I can have I want to write a 3-digit number. So let us, yeah, this is the other one and this is the other one. Okay, but you know that there are two problems, and 0 and 0 cannot be here. On the other hand, 0 sometimes can be here because I'm interested in even numbers. But this has the problem, you know that there is a problem here. I cannot put any number that I like here because I am not allowed to put odd numbers there. On the other hand, I have some problem here. 0 cannot be in this place. And there is a intersection between these two problematic parts. So somehow this will suggest me that might be it is better to separate these. So what I do, you can imagine it like this. You can say that, okay, I have this is the total number of 3-digit even numbers that I want to write. Some of them have 0 as the unit number, so assume that A, B, C is the number that you want to write. Some of them has, of course, C equal to 0. Yes, so here I put only those numbers so that C is equal to 0. The rightmost digit is equal to 0. And then the rest of it I put those numbers that are even 3-digit numbers where C is not equal to 0. This picture makes it clear. If I can count the number of elements in this part, and I can count the number of elements in this part, then immediately adding them using the sum rule will give me the answer, because there is no intersection between these two parts. I myself put numbers with the rightmost digit 0 here, and I put numbers with the rightmost digit not equal to 0. So this is not possible that something belongs here and here. Actually, these two parts, the intersection between these two parts is the empty set. Okay, so let me count this one and that one. So let us do it separately. For example, let me just say that the number of elements here is n1, and the number of elements here, I will call it n2. First, let me calculate n1. I want to write a 3-digit number so that the right-hand digit is 0. So how many options are available for the right-hand side is 1. Yes, the 0. I put 0 here, only I have 1 options. Okay, but from my list of numbers, 0 should be eliminated because I am not allowed to use 0 again because the repetition is not allowed. So if you don't mind, let me go here. So let me write this. I took this as stage 1, I will take this as stage 2, and I will take this as stage 3. Yes. So how many options are available for a stage 2 now? 0 is there. I don't need to be worried. What is left for me is acceptable for a stage 2. And how many of them are left? It's clear that there are 9 of them left. Okay, 0 was used here. One of the digits except 0 is also used here. I'm not allowed to repeat anything. So what is left for me for this third stage is 8 options. And then if I multiply them by the product rule, be careful again, don't be careless. This number should be independent, of course it is, but this number should be independent of the choice that I have made here. And it is clear that this is independent, so this tells me that the number of elements in the first part is 72. And now I want to go and count the number of elements there. Yes, so I will do the same thing here. So this becomes, I have again 3-digit number. I will keep, let us see if the stages are good to be something again as before. So what do I do? This time, how many options? I will take again this one stage 1, this one stage 2, and this one stage 3. How many options are available for this one? I want to have an even number in the first place, and I don't want to use 0. So there are only 4 options available for me. 2, 4, 6, and 8. Yes, 4 options. So it means that this can be accomplished in 4 different ways. Now, one of them is gone. For example, because repetition is not allowed. For example, 2 is gone. And then when I go to the second stage, 2 is already gone. I am left with 9 options, but 0 cannot be chosen there. So I am left with 8 options. Yes, so this becomes 8. Now, when I go to the next one, of course 1 is also here, but 0 this time, one of them is used here, but here 0 can be used again. So this means that I have also 8 options available here. And if I calculate this, it becomes 256. And finally, what I get, a question mark, is the sum of these two. N1 plus N2, which is 72 plus 256. And this becomes, as you said, 328. Yeah, is that understandable for everyone? This question is exactly at the level of the book. It's at the right level exactly. So you should be able to count this. But let me ask you one thing. If this part was not in the problem, repetition of digits is allowed. Do I really need to do this?
Probably not.
Okay, so then what would be the answer? Let us see. So let me just write with a different color. Repetition is allowed. So let me write like this. What if repetition is allowed? Of course, there is nothing prevent us to do it again in 2 steps, but let us see if it is necessary to do that. Can we just do it in one go? So let us see. I want to have a 3-digit number which is an even number. Okay, how many options are available here? 5 of them. 0, 2, 4, 6, 8. And then, of course, I am not allowed to repeat, but I'm allowed to repeat, but I cannot put 0 here on the left-hand side. So again, I want to keep this a stage 2, stage 3, a stage 1, and a stage 3. Okay, here how many options are available? I have 9 of them. And again, how many of them are here? 10. Yes? So do you agree with me that the answer now becomes 450? Agree? Everyone agrees?
Yes.
Okay. So you see that if you go back to my previous videos or your own notes, you will see that we solved the same problem. Even repetition was not allowed. I recommend you to go and review that. Repetition was not allowed. But we solved it for odd numbers rather than even numbers. Okay? So again, if you go to that problem, you will see that we still was able to solve it with one product rule by keeping the stages, the order of stages like this. But when it comes to even number, we were not able to solve it with one product rule. The reason is that I have 2 parts that interfere with each other in this case. 0 and 0 can be here for having an even number. On the other hand, 0 cannot be here because the left-hand side digit cannot be 0. So I recommend you to go back to refer to your notes there is an example that we solved. It was 3-digit odd numbers can be written if repetition of digits is not allowed. Exactly the same problem without having even. We had odd there, but we solved it only with product rule. We didn't need both of them. If you don't have any questions, we go to example 5. Okay, so let me see what is my answer I got. So what is yours?
225.
Anyone else?
I got the same.
Yeah, I also got the same. So 225. Okay, so we are good. How many 3-digit numbers are there so that each of them contains exactly 1 5? Okay, so by reading this sentence exactly 1 5, again, let me just draw some diagram like that for myself. So I want to draw a 3-digit a 3-digit number. But what do I want to have? Let me write the 3-digit number ABC. Am I allowed? I'm only allowed to put 1 5. Okay, so this means that I can choose that A is 5, or I can choose that B is 5, or I can choose that C is 5. Okay, and then first of all, this is the only possibility. There is no other possibilities left. At least one of them should be satisfied. And the other point is that there is no common number between these parts. These are completely disjoint parts. And then I would say that, okay, I will calculate n1, n2, and n3, and I add them, yes? And I will add them together. So, but for calculating n1, it means that the first number on the left hand side is supposed to be 5. So how many options are there? Only one. So I will take this as a stage 1, stage 2, and a stage 3. So I will have 1 options here. Here I have written how many numbers, so it is not mentioned something about repetition, so it means repetition is allowed. Okay, I cannot write 10 because I am not allowed to write 5 again. It has mentioned exactly 1 5. 5 is already used there, so this means that I have only 9 options here and 9 options here. So if I multiply them, it becomes 81. For n2 and n3, more or less the scenario is the same, but a little bit different from the first one. Yes, so I will have this one and this one. Here, how many options are available for the stage? So let me, this one, I will take this one as stage 1, and let me take this one as stage 2, and this one as stage 3. Okay, so stage 2, how many of them are there? 5 is used. I am not allowed to use it because I want to have exactly 1 5. 0 cannot be here, so I have 2 options. But here I have the only limitation that I have, I cannot use 5. So I can use all of them. And then the answer becomes 72. In the third one, what I do, I will change the stages again. I will take this one as stage 1, this one as stage 2, and this one as stage 3. How many options are for stage 1? Only 1. For stage 2, I cannot put 0, I cannot put 5, so I have 8 options, but then again the only restriction is that I cannot put 5, so it becomes 72. So the answer to this problem is the sum of these numbers, 81 plus 72 plus 72, which becomes equal to 225, and the answer is correct. So we can also put this in a box so that it can be easily seen. Okay, so this is probably the most tricky one. If you remember, if you go and watch the video, that was exactly the same number that I wrote on the board. But I want to hear from you what is your answer. If you could solve this problem, you are completely on the safe side. It means that you understood everything right. So be careful when you want to give me a final number. No one?
I got 572.
Anyone else?
got 2,544.
You're very closer, but no. Anyone else?
I got 2,646.
No, again, close but not. I might. You are very close, but probably you are making some mistakes. Yes, Khulud?
2,673.
Who is speaking?
Natalia.
70.
Free.
Okay, so no, the correct answer is 2,672.
No.
So I don't know how did you got these three out. So might be you have because there is no way to make such a one number mistake. Okay, anyone else? So you see that again, when I was solving some of those problems, you might think that, okay, these are trivial problems. First of all, if you read the question is very clear. Everyone understands what is the meaning in the question, but it doesn't necessarily mean answering the question is also very simple. How did you think about the problem? First of all, I want to write a 4-digit number. The lowest value is 1000, the highest value is 9999, but of course I want to have it greater than that, and the digits are distinct. First of all, I want you to think a little bit about that. If you do not want to solve this problem systematically, even though the problem is simple in nature, but it is really tedious and boring to start writing it, or of course you can do you can make a code with the program and then do it. Might be even if you want to do the coding, you need to understand how you need to count them. If you don't understand how to count them, probably your code will also not work. So that's also one thing that I want you to be careful about. I don't know what is your strategy to tackle the problem, but I always think in this way. Is there a possibility to solve this problem with one product principle? Apparently not. So I try to separate different scenarios. So I would say the diagram that I am drawing for you is because I always myself think in this way. I would say that, okay, I want to write a 4-digit number, A, B, C, D. So what I do, and I want this A, B, C, D all be distinct, and I want them to be bigger than this one. If I want to make a 4-digit number bigger than 1, if only A itself is greater than 4, then I don't need to be worried about other digits. Yes? Assume that this is bigger than 4. This is my strategy. I say that if this is bigger than 4, then I don't care about the rest. Every number that I start with a number with bigger than 4 definitely is bigger than that one, but of course I have to be careful not to count those with repeated digits. So I would say that, okay, one partition, I just give it one constraint. I would say that A is greater than 4. I will count all of them 4-digit numbers with distinct digits that the left-hand side digit is greater than 4. But of course, it is clear that the majority of them are here. So don't forget, these size of these parts are not into scale at all. I'm just partitioning them. But it is, I hope that intuitively clear for all of you, the majority of the numbers that I want to count actually lie here. Yes?
What was the answer again?
2,672.
Okay, I still have a button.
Okay. So this is one part. The other part is, what can I say for the other part? I would say that, okay, not all of them are being considered in the first part. There are some of them so that A is still 4, but B is greater than 7. Then still I am on the safe side. Yes, because A is 4, but b is bigger than 7. If a is 4 but b is, for example, 8, who cares about the rest? This number is definitely greater than that one. So that is also one thing. I think now its strategy becomes clear, yes? So the next one is, I'm not saying this, again I'm repeating, these are not into scale. I would say that, okay, another type of numbers is that a is 4, b is 7, but c is greater than 2. Yes? So if a is 4, b is 7, and c is greater than 2, say 3, nobody cares about the first digit. This is definitely bigger than that one. And finally, I consider this case that a is 4, b is 7, c is 2, and d is greater than 1. Okay? I hope that you agree with me that this is all possible scenarios. This is one thing that I want you to understand. First of all, I want you to understand, if I consider all of them, that is the all possibilities in front of me. This is one thing important to understand, but I would say more importantly is to understand that there is no intersection between any pairs of these parts. And that is also clear, because I am telling you, I put numbers here so that a is greater than 4. But I am telling you that the numbers that I put here has a equal to 4. So there is nothing here in common between them. There is a 4-digit number here where the left-hand side digit is greater than 4, but here the left-hand side digit is 4. Of course, I have extra conditions, but who cares? The numbers here and the numbers here are totally different. And the same scenario here. So this is, you have to convince yourself that there is nothing in common between these two pairs. Nothing in common. So then, if this is true, then it means that I can use the a sum rule to calculate each one of these parts, and then what to do, and then add them at the end. But then it becomes hopefully clear now that for calculating each one of them, I have to use the product rule in an effective way. So what can I do? I would prefer, let me write this list: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let me copy it once for all, so might be I have to repeat it. A copy, okay, so let us see what happens. And then I will go to N1. N1. So I have 4 digits to consider. I don't know, let us see which stage you want to call stage 1, which one you want to call stage 2. Yes, let us see how this will work. Which one I call stage 1? I would say that this is a stage 1, stage 2, stage 3, stage 4. Okay, now please tell me, A is supposed to be greater than 4. So how many options are available for S1? 1, 2, 3, 4, and 5. So I have 5 options available, but because repetition is not allowed, one of them has to be crossed over. Okay, so for example, which one? Of course, you need to also be careful about this point. So one of them I just cross. One of them numbers greater than, let us cross 8, for example. So it means that I used 8. And now I don't have anything to be careful about except repetition is not allowed. So how many options are available for S2? There are 9 options, because any number left in my list can be used. And then how many options are available next is 8, and how many options next is 7. I used my calculator to multiply them. This becomes 2520. And that is exactly, I told you that this is intuitively correct. Most of the numbers that I am looking for are there. So let me call this one stage 1. Let me do one more thing. Let us paste it here so that you are not confused. Let me make it a little bit closer so that we have enough space. Okay, so here, now we go to stage 2. Stage 2, sorry, the second part. The second part, I will also keep the stages exactly as before. I think the order of stages are actually good for all of them, if I remember correctly what I did. So, stage 1, how many options are there? I want to put 4 there, so there is only one option here, stage 1. Okay, so what does it mean? It means 4 is gone, because repetition is not allowed. But b should be greater than 7. This is 7. Greater than 7, I have 2 options, so I put 2 here, but one of them is also gone. Yes, one of them is also gone. Which one do you want? For example, let us cross 9. And then when I go to a stage 3, it means that how many options now are available for me? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 options available, yes? And for for the next one, how many options are available? Clearly 7, because one of them is also gone. And I multiply that, the answer I got is 112. And then I go to number 3. So number 3, again, I have 4 stages. Yes, and I think again the order of the stages is actually good, so I will choose this one, stage 1, stage 2, stage 3, and stage 4. But let me, yes?
I managed to find the bug and I
Okay. Okay. So yeah, at least that's good.
Because
that
I was counting without distinct digits. That's why.
Okay. Okay. So here, this is the other one. So here, N3, when I go to N3, A is 4, B is 7, so it means that there is only one option here and one option here, but 4 and 7 have to be crossed over. 4 and 7 are gone. But when I go to S3, I can choose, okay, sorry, yes, I have to be careful. C is supposed to be greater than 2. So this is the tricky part probably. When I have already crossed these two, I want to choose C greater than 2. So in my list which is left, 1, 2, 3, and 4, and 5 of them are there. So this is 5. And one of them is gone now, so let me cross it over. And what is left for me, again I missed the colors. So this is 5, and then another one is left, so it's, how much is left now? 7, yes? Yes. And that is 35. And we go to number 4. I have again 4 stages. Yes, 4 stages. Stage 1 again, stage 2, stage 3, stage 4. And if you don't mind, let me just paste one more here. And then number 4. Let us see now how this will work. Here, A is 4, B is 7, C is 2. So it means that I have one option, one option, one option. But I have to cross them over. 4 is gone, 7 is gone, 2 is also gone. And then I need to have D greater than 1, but from the leftovers. So 1, 2, 3, 4, 5, 6, and 7. So boy, 7, in the first counting I got 5. Do you see my flaw? Ah, it should be bigger than, sorry, it should be bigger than 1. I don't know why. 1, it should be bigger than 1 from the leftovers. So 1, 2, 3, 4, and 5. Yes. Might be you also not only did mistake at this part, I don't know. This is 7. So again, I made a mistake, you see. The answer is 5, so the answer becomes 5. Then I have to add them all. So this becomes 2520 plus 112 plus 35 plus 5. And the answer turns out to be 2672. Okay, so I would say that this is probably the hardest problem in this set of exercises. Any questions here? I don't want to continue. I suddenly realized that we ran out of time, but can you give me the answers to the other questions to check if it is correct or not? Did you get
for
the
7 I got 31, and for 8 I got 204 squares.
I got the same answers for both.
For 8 you are right. I also got 204. But what you said about 7?
For 7 I got 31, because for like vertical rectangles there are 15 combinations, and for horizontal there are 16.
So might be I have miscalculated. I don't know. 3 rectangles are there in a 5 by 6, 2 by 3 rectangles. So 1, 2, 3, and then 1, 2, 3. So I got 9 horizontal one. I don't know why you say that. The answer that I got is 19. Might be I am wrong. Let me see. 1, 2, 3, 4, 5, and then 1, 2. So I get 10 vertical one and 9 horizontal one. Yeah, we can. I don't know. I have to check that one. But for the last one, because I know the formula, so you are right. The answer to that one is 204. And if you could solve this one, in principle, your solution is correct here. Might be. So because they are exactly of the same type of they are of the same type of questions. Okay. But let me check that one later. I will discuss about that. So I would recommend you, if you haven't solved these 2 problems, when I uploaded the video, you will find the link of this PDF file below the video. Please try to think about these problems together with the problem that is left from the previous session. Do you remember I told you that prove that the number of subsets of any set that contains even elements is equal to the number of subsets that contain odd elements. Okay? Yeah, that is also something that's very good to know. Okay, thank you, and sorry for